So that was about the trapezoid rule. Let's look at the next algorithm for doing numerical integration, and this is called Simpson's one-third rule. Now in the trapezoid rule, so once again let's take some x and some f of x. So in trapezoid rule, what we did was we divided up this integration range into slices, and then within each slice we approximated this to a straight line. So we made trapezoids. Now instead of drawing straight lines, we'll say what if we make a quadratic function. So a straight line is a linear function. What if you go to a x square kind of a quadratic function? Will that give us better results? So over here, let's say if you take, remember that to define a straight line you need 2 points. To define a quadratic function you need 3 points. So 1, 2, 3. Suppose I define a quadratic function over here, something curved. Will this give me a better answer? That's a question we are trying to address, and that will lead us to what we call Simpson's one-third rule. So let's just take these 3 points. I'll take this out. So suppose these are xi, xi plus 1 and xi minus 1. Or I can say this is xi, this is xi plus h, and this is xi minus h, because the spacing between each of them is always h. So you will notice, so suppose the function, this yellow function that I want to define to fit to this curve over here, suppose this function is ax square plus bx plus c. So then what I'm basically saying is that at this middle point, the function f of xi has to be a xi square plus b xi plus c. The function at xi plus h is a xi plus h square plus b xi plus h plus c. And similarly for the previous point, xi minus h, this has to satisfy this equation. Now notice that in general, if suppose 0 x fx, so suppose these are the 3 strips that I was talking about, the 3 slices I was talking about. It doesn't matter where these are located, no? Because instead of them being located over here, if I had just moved them over here to the anywhere else along the x-axis, the area under this curve over here still remains the same. It doesn't matter where it lies. So I can say, just for simplicity, let me just put them over here at the origin, right? So, or in other words, what I'm saying is, over here when I say f of xi plus h, f of xi minus h, over here, instead of, I can just pretend that xi is 0, and I will still get the same formalism for the area under the curve. So let's do that. So I'm going to treat my xi as 0. So f of 0 is just c, f of h is just ah square plus bh plus c, and f of minus h is ah square minus bh plus c. Now these are 3 equations in 3 unknowns, a, b, c. You can evaluate what a, b and c should be. And I will just write down the answer since I have it ready over here. So if you solve these, you get a equals 1 over h square f of h plus f of minus h over 2 minus f of 0. B turns out to be f of h minus f of minus h over 2h, and C is f of 0. So these are the solutions for A, B and C. So now the area of these two slices defined by this quadratic function is just f of x from minus h to h, which is a x square plus bx plus c. But this is so integral of x square is x cubed by 3, integral of x is x square by 2, integral of c of constant is just x, evaluated from minus h to h. And so now if you just plug in, so first of all, of course, you will put h and minus h, so you will end up getting uh, 2/3 ah cube. The b term doesn't play a role because it's the same for h and for minus h, and 2ch. And we already know what a and c are because we had calculated them. So this is a and this is c. So you can plug those in and you will get this. So of course here we had taken that these slices are sitting at 0. That doesn't have to be the case. In general it can be at any xi. So in general, so this is area of two slices from minus h to h. If your slices were from xi minus h to xi plus h, then this would be h by 3 xi minus h xi plus h. And now the total integral that we are interested in, which is integral from a to b, this is just sum over all of these two slices. So this turns out to be, let me write it from here. So if you start from 0, then you get, so starting from here, first you will have f of a, then which is x0 by the way, then you have 4 times f of x1 plus f of x2. This is the first set of two slices. But the next set of two slices gives you f of x2 plus 4 times f of x3 plus f of x4. Then the next set of two will give you x4, 4 times f of x5 and x6. And then you keep going like this, and then in the end you will have the last one, n minus 2, 4 times f of x n minus 1, and f of xn, which is just b. So now you will notice that here this 2 comes, x2 comes twice, x4 comes twice, and so on. So all the even numbered contributions are coming twice. All the odd numbered contributions are already here and they have come 4 times. And then of course there is the first one and the last one. So I can put these together and I can say I is h by 3, f of a, f of b, that's first and last point, plus 4 times sum over all the xi's where I are odd, plus 2 times sum over all the f of xi's where the i's are even. So this is Simpson's 1/3 rule. 1/3 because this 1/3 appears over here in front of it. Of course, needless to say, the total number of slices over here needs to be even because you're taking 2 slices at a time. So in the end, the number of slices should be an even number. So this gives you a slightly more accurate answer compared to the trapezoid method. And let's discuss how we know that. So we are going to discuss what is probably one of the most important aspects of any kind of numerical approximation like this, which is the error analysis. So in error analysis, what we want to know is, we've run some approximate method to calculate this integration. How close is it to the actual answer? We want some estimate of that. Of course, when we say error analysis, we are just finding out what is the maximum possible error we might have had. We never know exactly what is the error. If we knew what is the exact error, then we would know what the exact answer is. But because this is an approximate method, we can only estimate what the correct answer is, and then we can estimate how far we might be from the actual answer. So that is what we mean when we say error analysis. So just for simplicity, we are going to do error analysis for the trapezoid rule, but you can do it similarly for the Simpson's 1/3 rule as well. So consider the bin from xi to xi plus h. So this is some trapezoid over here. So area of this trapezoid, ith trapezoid, is, as we had discussed, half times height times f of xi plus f of xi plus h. Now on this f of xi plus h, I am going to apply Taylor expansion, Taylor series expansion, which we saw before in the introductory lecture. So this becomes f of xi plus h times df by dx. So there's one notation I will use over here. I don't know if you have come across this before. So derivative is written as f prime. Second derivative is written as f prime prime, and so on. So you just keep putting as many primes as there are, as many times as you are differentiating it. So h times f prime at xi plus h square by 2 factorial f double prime at xi, and so on. In fact, I'm going to write over here plus order of h cube. So this is again notation, which means that this means order of h cube. So it means there are other terms over here of which I'm neglecting. Of all those terms that I'm neglecting, the most significant one is h cube. So this is going to have h cube term, h to the 4 term, h to the 5 term, and so on. But because h is a small number, h cube is the most significant or the largest of these. Everything else is even smaller than that. So order of h cube means there is an error which is at least as large as order of h cube, if but not more than that. It could be smaller but not more. So this is our Taylor expansion. So here we have f of xi plus f of xi. So I get h by 2 twice fxi plus h f prime xi Okay, so this is area of this one trapezoid. But now let's try and find what the actual answer would have been. So suppose this function f that I'm trying to integrate, suppose integral of this is given by capital F. So then integral from, where is this from xi to xi plus h is going to be f of x from xi to xi plus h. So this is f at xi plus h minus f at xi. Now again for this fellow also I can do Taylor expansion. So this becomes f at xi plus h times f prime at xi plus h square by 2 factorial f double prime at xi and so on, minus f of xi. So now you notice this f of xi cancels out and I'm left with this. So this is my approximate calculation based on trapezoid rule. This is supposed to be my exact answer because this has come from this actual integration formula. So the error, and sometimes it is denoted by epsilon, is given by the difference between the two. So what does the difference between the two turn out to be? Wait, before I do that, capital F is the integral of small f. So when I say f prime, the derivative of that has to be f itself, small f. So this is h times small f x plus h square by 2 f double prime blah blah blah. So now the error, which is the difference between these two. So if this is called AI, this one let me call II. So the error is given by AI minus II. This is error in the ith bin, by the way. So notice over here the first term in AI is just h times f of xi. In II also the first term is h times f of xi. So that cancels out. So the next significant term that remains is proportional to h square. So it is h square times something. And this is the important thing to note. The important thing to note is that over here, you have h square terms and you have higher order terms. Actually, I think h square also cancels out. So f double prime xi over here is just small f prime xi. And that also appears over here in the AI formula. So when I take the difference between AI and II, it is not only the h term that cancels out, it is also the h square terms that cancels out. So in the end, the only thing that remains is this h cube term. So h cube by Here there is h cube by 4 f double prime, and over here there will be also some well, something in terms of h cube, probably not the same, because over here you also have a factor of 2 coming in from here, so this is 4, and this is, oh, this is going to be 1/6, so minus h cube by 6, because 3 factorial f double prime xi. So 1/4 minus 1/6, that is 15 minutes minus 10 minutes is 5 minutes, so 1/12. So h cube by 12 f double prime xi. So this is the error in each bin. It is proportional to h cube. So the overall error across the entire a to b integration, you can just hand wavingly, approximately, this is going to be of the order of h cube by 12, so this was already there, times n, because there are n bins. So in each bin, if the error is of this order, then the total is something like this. But if you remember, n is just b minus a over h. So one of these h's cancels out, and you get h square. So the error in whenever you calculate the integral using trapezoid rule is of the order of h square. This is an important point to remember. So again, this shows that the smaller you make h, the more accurate your answer will be, because your error will be smaller. Similarly, one can do this kind of error analysis also for Simpson's 1/3 rule. And it turns out that in this case, the total error turns out to be of the order of h to the 5. So it's much more accurate than the trapezoid rule. So in general, if you have a choice between trapezoid and Simpson, it's much better to use the Simpson's rule. Okay,